Hey, good morning.
Morning, or
It took me so long to find the buttons to come back to the room so I could unmute myself.
yeah, sounds good. Yeah, for me it is 1 minute afternoon, but
True, true,
back for a bunch of us, it's still morning.
true. I mean, for some of us, it may be evening.
Could be.
I
Yeah,
actually don't know where a lot of.
yeah. Neither do I. Yeah, typically a lot of variation. All right, Abby, are we? Should I do a little like my normal? Here's what we're going to talk about today. Thing. Are we
I think
planning on?
so.
Okay, maybe in the future we'll kind of prepare
I
that.
agreed. Yeah,
Okay.
but for now, feel free to wing it. I think a little bit of overview is always good for all of us.
Great. Okay. All right. So I'll get started. So I think just a brief reminder what we talked about last time because it's been 2 weeks now. I think I was traveling last week. We covered Marlin, and sort of compared to Spartan because you can view both of these as snarks for R1CS, and very broadly, Marlin has nicer verifier costs. But Spartan has nicer approver costs. And, the verifier costs in Spartan are still like pretty decent. But, if you had a choice, you would certainly rather have Marlin proofs on chain because like your gas costs will be lower noticeably. Maybe Marlin is like a kilobyte or two in proof size, and Spartan, depending on your commitment scheme, is out of, let's say, 3 to 10 kilobytes, and kind of the GKR protocol, depending on application, may have an even faster prover yet. So sort of depends on certain specifics of your application, so maybe even faster, but definitely has bigger proofs than Spartan. GKR, you're thinking like, I don't know, 10 to 20 kilobytes per application of GKR, and a lot of protocols might apply GKR multiple times or something. So that's a very brief recap of last time. Okay, so today, I unexpectedly decided yesterday, chatting with Abby, we're going to discuss lookup arguments. And this will sort of be our last. So we've been talking about in general what are called polynomial IOPs, or PIOPs for short. I've never really said necessarily in detail what is a polynomial IOP, but that's what we've been studying. So, Spartan and Marlin are polynomial IOPs. And you can turn them into a snark by combining them with any appropriate polynomial commitment scheme. So today will be like our last session talking about different polynomial IOPs, in particular different lookup arguments.
I wanted to ask a quick question there. So you mentioned that Marlin and Spartan are they're PIOPs, and so they're not complete snarks. They're only part of what you need for a snark, and then you have to pick the other piece of polynomial commitment scheme separately.
Mm-hmm.
Is that right?
That's right. And yeah, and that's exactly right. So elaborating a little bit, like when you're optimizing for verifier costs, you typically want to use KZG commitments, typically, if you don't mind the trusted setup and pairing friendly groups, because that's what's going to lead to the shortest proofs and fastest verifier. So Marlin would be typically combined with KZG commitments. If you don't like the trusted setup or the pairings, you could maybe combine it with bullet proofs. Like Zcash, they're not using Marlin specifically, but that's what they use as their polynomial commitment scheme. That has its own like pretty nice short proofs, but slow verifier. Also a somewhat slow prover. Some projects will combine something like Marlin or Planck, which has similar-ish cost to Marlin. With Fry, Fry just uses hashing, no groups. It's another polynomial commitment scheme. My view is the proofs in Fry are big enough, like say close to 100 kilobytes, maybe even more, maybe a little bit less as work continues to optimize it, that it really doesn't make sense to use a PIOP like Marlin or Planck with Fry. At that point, you should use something sumcheck based, right? Because sumcheck is really good for the prover. People are starting to come around to that claim, even though it's been somewhat controversial. Once you have logarithmic size proofs coming from sumcheck, or once you have polylog size proofs coming from Fry, you might as well pay for the log size proofs from sumcheck, because they don't really matter. They're not a bottleneck in verifier costs anymore. Anyway, so I think Spartan and GKR makes sense to combine with a wider class of polynomial commitment schemes, not just KZG or bulletproofs. Just because they're not focused on, like, generally the reason to use Marlin or Planck or Growth 16 is when you want really, really low verifier costs. And so it generally makes sense to combine those with these polynomial commitment schemes with like really short, really low verifier costs. Whereas Spartan and GKR are not so focused on verifier costs. You sort of, are free to use other polynomial commitment schemes that, are not as good for the verifier necessarily as KZG or bulletproofs. Was that helpful context? Not too confusing?
That's great.
Okay, great.
I don't have any follow-ups. We did have one question, so Nicholas, do you want to ask?
Hi, Justin. So I have two little questions still on RNCS and Marlin, if I may.
Quality is terrible. So sorry.
Your audio is pretty bad, unfortunately.
I'm sorry.
Do you want to try to type what? Yeah, feel free to type them out in chat.
Okay. Let me give a quick overview of what we're going to cover today, and then maybe Nicholas will have the question typed out or have the audio fixed. Sorry, Discord is annoying with the audio. So lookup arguments, again, they're basically polynomial IOPs, and you can combine them with any polynomial commitment scheme. And which one you want to use is going to depend on, are you optimizing for prover costs or verifier costs? Are you willing to use recursion somehow to bring the verifier cost down further? If you're not happy with the verifier costs, initially or something. So after today, we're sort of done with polynomial IOPs, and we'll move to, ultimately, I want to cover polynomial commitment schemes, but in order to cover that, it sort of makes sense to first discuss zero knowledge. Actually, mainly, it's this funny thing. So next time, or the coming weeks, I actually would be very happy to talk about zero knowledge, like as the very last topic in this, reading group. But a lot of important polynomial IOPs are built out of something called Sigma protocols, which are very simple protocols that I view as sort of building blocks for general polynomial commitment schemes. The funny thing is Sigma protocols don't really, they're not very interesting on their own if you don't care about zero knowledge. So it's this weird thing where I want to talk about Sigma protocols because I care about polynomial commitments, but you won't really care about Sigma protocols as standalone objects unless you care about ZK. So the order goes ZK, then Sigma protocols, and then various polynomial commitments. So that will be the plan moving forward. Okay, so I will start telling you what lookup arguments are. Let me just pause and see if Nicholas's question is ready by any chance. We can also take it later if there are any other questions.
Nick typed out one of the questions. I feel like it's kind of out of scope, though, and I actually don't want to take that digression.
Okay.
The second question just came in and actually does feel its scope. So for Marlin, you mentioned that it uses a universal trusted setup. I don't see where this comes in yet. Is it only part of the polynomial commitment scheme?
Yes, exactly. So in Marlin, if you use a transparent commitment scheme, meaning one that doesn't need a trusted setup, there just will be no trusted setup at all. and so in everything but Grow 16, like whether you have a trusted setup and also what cryptographic assumptions you wind up, basing security on, that's all coming from the polynomial commitment scheme. And so the reason Marlin has a universal setup is basically because KZG commitments are used to commit to any polynomial up to a given degree bound. And so the trusted setup, you sort of, can run it once, and then you're capable of committing to any polynomial up to the associated degree bound, and that is enough to run Marlin on any constraint system, any circuits, any R1CS instance up to a given size. And so Growth 16 is this somewhat odd outlier where it doesn't quite fall into this design framework of polynomial IOP plus polynomial commitments. It's like very close, but not quite in that framework. And therefore, it's sort of also unique in having a circuit-specific, constraint system-specific setup. So that's what's going on. So like if you combine Marlin with bulletproofs, there's no trusted setup. Was that a clear enough answer?
Yes. And we have another question from Skanov.
Yes, hello. I wanted to continue the previous question. I wonder if what is the best way to put it? For different size of the domain, for different size of domain, for different number of roots of unity. Is it possible in this setup to use the same coefficients, or would it ruin the security? I mean, in the previous lecture, you showed that columns and rows numbers could be different, hence they would need a different domain for roots of unity. And I wonder if the setup for the bigger roots of unity set can just extend the previous one, or should it use entirely different elements or scalars in it?
Great. Good question. The high level answer is one single powers of tau setup should suffice for all constraint systems up to a given size bound. And so if your constraint system is smaller than that, like it's not like you need a different trusted setup. In fact, you could just, it's like, what is this SRS? It is g to the tau squared up to g to the tau to the degree bound. And here this tau is toxic waste. If anyone in the world knows the tau, they can produce convincing proofs of false statements very easily. And so if you want to commit to polynomials of degree lower than capital D, you can just sort of ignore the extra powers. So if you want to commit to a polynomial of degree D-1, you just sort of ignore that last power tau. Then there is a question of what if the polynomial IOP really, really, really requires that the polynomial that is getting committed, has degree, at most D-1, and committing to a degree D thing would somehow break soundness of the PI-IOP. Degree D, would be bad. Break soundness. And there, we have techniques to deal with that. So firstly, offhand, I'm actually struggling to come up with why that would be an issue. But I do think I know I've seen papers that address it. And roughly, if I remember right, the idea is if you want to force somebody to commit to something of degree D, you kind of, or something of degree, let's say little d, which is less than big D, I think you can take whatever they commit to, say, the committed thing is P of X, and just multiply it by X to the capital D minus little d. And now, it's like if P has degree more than little d, then this thing will have degree more than big D. And, like the standard, property of KZG with this SRS, up to power capital D will apply. So people have looked at that. Although again, offhand, I don't even remember why it's really necessary in soundness to prevent somebody from just always committing to something of, why soundness in any PIOP would break if they commit to something of capital D degree rather than little d. Yeah. And then as far as the roots of unity stuff, the need for roots of unity is really coming in for two reasons. One is certain operations in the PIOP will only be fast, may only be, fast if you work over roots of unity as like the interpolating sets or whatever. Because you, in particular, well, just as one example, these univariate polynomials and these univariate polynomial based snarks or PIOPs like Marlin or Planck or whatever, they often need to do something like polynomial division, or they need, the polynomial is like kind of handed to the prover in the Lagrange basis, and they need to transform it to the standard monomial basis to use the powers of tau setup or something. And those transformations, fast polynomial division or basis transformations, really, they want to use FFTs, and FFTs work nicest over roots of unity. And then the only other reason you might actually need the roots of unity thing is because, again, if you use the powers of tau setup, you really want, so KZG commitments themselves, generally they want, the polynomial to be committed to be in the standard monomial basis. And again, the polynomials typically kind of handed to the prover in the Lagrange basis. So that transformation also it will only be fast if you have these roots of unity in the field you're working over. There have been some works that I think we discussed briefly in some earlier sessions that kind of modify KZG to work directly in the Lagrange basis. So in that case, maybe, it's only the PIOP and not the KZG commitments at all that really need the roots of unity. So that was a long way of saying, up to some details that are not that hard to overcome, kind of one powers of tau setup, for 1 degree bound works for all constraint systems, Marlin for our constraint systems or whatever, up to a size bound rather than exactly equal to a size bound. Did that make enough sense?
That's an interesting answer. Thank you. Since my question was coming from the supposition of that the degree of the setup helps to ensure that a committed polynomial is of something, is of that degree. But I'm absolutely not sure that that I'm having the correct view on this thing.
Yeah. No, I think if the trusted setup has, capital D powers of tau in it, then, anyone can commit to a polynomial of degree to that degree bound, but no higher. And so, if you want to force the prover to commit to something of strictly lower degree than capital D, there are ways to do that, but you do have to, do some extra stuff, multiplied by this monomial thing or whatever. And I'm punting on the question of like, why would you ever really, really need the prover to commit to something of degree strictly less than capital D? Again, off the top of my head, I'm actually blanking on why you would need that, but I remember it's come up at some point in some papers, and people have cooked up these techniques to deal with it.
Yeah, that adds a lot of sense to the to the question, to the problem. Thanks.
Great. All right. So let's talk about lookup arguments, but feel free to interrupt as always. Okay, so let me tell you what is a lookup argument. Okay, so actually they come in two different flavors. I call them indexed versus unindexed. Okay, and most of the literature actually focuses on or defines the problem to be unindexed. I actually really prefer indexed. So let me just tell you what they both are. They're both very natural problems, and then for the most part, we're going to focus on indexed today, but I'll say a little bit more about the relationship between them. Okay, so indexed is the the prover has already committed to, or someone has already committed to two vectors, say A and V in field of the M. And there is, so this is sort of this is sort of the setup, or what like the problem statement or something for lookup arguments that they're solving. And there's some predetermined, meaning like both the prover and verifier know what this is. Call it a table or an array, T, and I like to call it of size. Well, let's just say it's in field to the N. So it's in capital N. So it's a table of size capital N, table of field elements. Okay, let's not worry right now about if N is big, let's not worry about how the verifier, knows what T is. It will, yeah. So just somehow the verifier knows what T is. In general, it might be possible for the verifier to kind of know what T is without actually spending time capital N if T has a implicit description, like if it's all numbers between 0 and n-1, the verifier does not have to literally write down all numbers between 0 and n-1. Okay, so that's the setup. And what the prover wants to prove is that for each of the M entries of A and V, we have that the ith entry of V is the ith entry of T. Yeah. So we call these the AIs, we call these indices, table indices, and the V's we call values. And so what this is just an index lookup argument is literally the same as a read-only memory. Right? It's like the table is just a pre-initialized memory. Memory cell index 0 has some value stored in it, T of 0. Memory cell 1 has some value stored in it, T of 1. And the prover, just commits to, indices and values, and it's claimed that, the ith value is the table element in the ith index. and that's the, so yeah, we're doing lookups into a read-only memory, also known as a lookup table. Okay, that's an index lookup argument. Okay, any questions about that definition? All right, and then unindexed lookup argument. Here, there is no vector of indices. So there's just the committed vector V of length M, and the claim is, what the prover wants to prove that is that for each entry of V, there is some index, say J, such that VI is T, the jth entry of T. So this is like, you want to prove that every committed value lives somewhere in the table, but you don't care where. Okay, and so if you view if you view V as a set of values and the lookup table T as a set of values, the claim is that like V is a subset of T. Or ignoring duplicates, obviously, like maybe if the zeroth entry of T is the field element 782, it's fine for 782 to appear many 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 times in V. I would still call V a subset of T in that case, as far as this notation or terminology goes. So unindexed lookup arguments are kind of like subset claims. And index lookup arguments are like read-only memory claims, valid reads into a read-only memory. Okay, questions about those definitions? All right. So
I think there might be one question here.
Oh, please.
Just added someone to the stage. Let's see. Go ahead. I don't hear you, but it looked like you unmuted. Yeah, I'm not getting any audio. Are you, Justin?
No. So, okay, I'll continue, but feel free to try again soon.
Cool, I'll let you know.
Discord, all sorts of issues. Okay. So which version you want depends on your application. I find that ZKVMs, which is sort of like the main thing I think about these days, you really want indexed lookup arguments for the most part, and I can say more about that later. But both are natural variations. And the other thing I'll say is there are decently efficient and simple transformations between the two. These transformations are not without any overhead. If you take an unindexed lookup argument and take it into an indexed one, the prover will do some more work, but it's not a huge amount of extra work. If I give you an unindexed lookup argument, I am implicitly also giving you an indexed one, but there will be some extra expense in the indexed variant than in the unindexed variant. And similarly, if I give you an indexed one, you can kind of throw away the indices and make it into an unindexed one relatively straightforwardly as well. I'll leave it at that for now. And I want to cover an alternative view of index lookup arguments, which is not a widespread view of index lookups, but I think it's a valuable one. Let me just tell you the next 2-3 minutes of this presentation. So first, I'm going to give you an alternative view, an equivalent definition of index lookup arguments. It's just a perspective thing, and then I'm going to give you two different naive solutions to index lookup arguments. And then we'll go to the interesting lookup arguments that I want to actually tell you about today, and why they improve over the naive solutions. All right, so here's an alternative view of index lookup arguments. So say the entries of the table are all evaluations of some function. So that is say the table size, capital N, is 2 to the little n. Okay, and let's say f be a function on n-bit inputs, little n-bit inputs. Okay, and say that the axis, so now you should be used to this at this point. I'm indexing table entries by bit vectors. So I'm indexing the capital N table entries by little n length bit vectors, just rather than by integers, and say that the axis entry of the lookup table is just this function f evaluated at x. Okay, then what is a lookup what is an index lookup argument then? I would call it, so remember, an index lookup argument lets the prover, commit to indices and values, and prove that the ith entry of V is the AIth entry of T, which is the same as the F evaluated at AI. So, okay, I guess I'm, here I'm doing the opposite, I suppose. Here, okay, so let me be explicit here. This would be the binary representation of the field element AI. Okay. Yeah. Sorry for.
I wanted to ask about that because I was wondering, is the elements AI are actually coming from the same field? Because they're indices, they're not like field elements. And so like if they have to come from the same field, then that means that your list can only be as long as the field and like other things.
Yeah. So right. So great question. Thank you. So almost always let's just say we're working over a huge field right now, 256-bit field. So our table is going to be smaller than the size of the field. Okay. So let's say, the table size, I don't know. Let's say the table size is 2 to the 16. Field size is 2 to the 256. All right. So your table is much smaller than the field. Okay. But it is this funny thing where, the indices, as I defined the notion of a lookup argument, are field elements. Let's say it's a prime order field. This is just for concreteness. It doesn't have to be the case. So the indices, though, the entries of A are field elements. Okay, and what we're doing here is we are like kind of interpreting field elements, 0 up to 2 to the 16 as like indices for the table. Okay. And what we're gonna, so we do demand out of our lookup arguments that, if any index in the, committed indices AI is like not in the subset of the field 0 up to 2 to the 16 minus 1, then, the prover is going to get caught. So let's say the verifier is going to reject no matter what. So it's sort of amazing that you can do this, right? Like it's a little awkward to, field elements are not integers, although they kind of behave like integers model large prime if you're working over large prime over field, but they're not literally integers. And yet in these lookup arguments, we are sort of conceptualizing the indices as integers, indexing the table. What's really going on is like whenever we design snarks, we're kind of free to index, entries of vectors. The table is just a vector by anything we want, whether it's a subset of the field or binary vectors or whatever. And so the definition of a lookup argument is naturally indexing the table, indices with a subset of the field. But then this alternative view I'm giving is, kind of actually indexing the table by bit vectors, sort of log table size, many bits in each vector. And snark machinery just happens to be pretty good at seamlessly going between the different ways of indexing vectors. But it's kind of amazing how it works out. At least sometimes it's a pain and adds overheads. Other times it just is kind of costless to move in between different ways of indexing vectors. So anyway, hopefully that answered the question. In the definition of a lookup argument, the indices are field elements, and we are just indexing the table in this definition by a subset of the field. Does that make sense?
Yeah, totally. Thanks.
Great.
Yeah, that's it for now.
Okay, cool. So, yeah, okay. So in this perspective, this alternative view of index lookup arguments, what the prover is proving, right, is that f, this function, was evaluated at many, many different inputs, a1 up to am, correctly. Yeah. And so from this perspective, what an index lookup argument is just it's an efficient snark for what I would call like super data parallel computation, where you are just evaluating the same function over and over and over again. Okay. And so what's going on is in our lookup arguments, like the prover cost in our lookup arguments will be some cost that depends on the table size only, plus some per lookup cost. Okay, so like in what I will talk about what I would call basic lasso today. Don't worry about what basic lasso. If right now it's kind of the simplest variation of lasso. What the prover cost is roughly like capital N, okay, plus say 3 times number of lookups. So what this means roughly is like the prover commits to sort of one field element or something per table entry, roughly, something like that. Maybe it's 3. I don't remember offhand, and it depends. Yeah, on the setting. And 3 field elements per lookup. Okay, so what's going on is you sort of pay a big upfront cost based on how big the domain of little f is, this function you're evaluating over and over and over again. But then that cost is sort of independent. It doesn't matter how many lookups you do into this, how many evaluations of f you do. Okay, so in particular, if you do way more evaluations of f, then the size of its domain, basically, so you're gonna, that means you evaluated it at some inputs many times. You're sort of, coming out ahead. Like basically, as long as your per lookup cost is really cheap, it doesn't really matter, and you do enough lookups, it doesn't really matter that you paid something for the size of the table. And in fact, okay, so if you go beyond basic lasso to generalized lasso, so more general lasso, more general than basic lasso. Okay, you can actually, in general, sort of, and there are some caveats to just how general it is, but you can reduce this cost to something like, for any c greater than 0, this can fall to like order n to the 1 over c plus 3 times c times m. So what this is saying is you can reduce, to sublinear in the table size. So reduce the cost that depends on the table size. So like table cost to way below table size. You do, yeah. This doesn't apply to like every table in the world, but it does apply fairly generally. And at the expense of kind of increasing the per lookup cost. Okay, and so coming back to this like highly data parallel, super data parallel, snark for super data parallel computation situation, what's going on is, you sort of in the lookup argument, you kind of you pay some cost that depends on the size of the domain of the function you're evaluating over and over again, but you can kind of drive that cost fairly low at the expense of making the per lookup cost higher, and then ultimately you're able to prove each evaluation of f with kind of a, if you think of c as a constant, like 2 or 3 or 4 or 5, with like a constant cost per evaluation. Okay, so that's how you to think of lookup arguments. Is in general, there's like they're really good for in amortized settings, so they always have some cost that depends on the table in some way, on the size of the table. Okay, but then if you do a ton of lookups into that table, you're able to amortize that cost, that did depend on the table size, effectively across all those lookups, and therefore in total across all the lookups, you can get the cost to be pretty low. So it's all about amortization. Like you really, lookup arguments are only interesting if you're doing many lookups into a table. Okay. Let me think what else I wanted to say. Yeah, so I think that's actually a good segue into the two baselines, like two naive solutions. But maybe it's a good. I don't think I presented this perspective of a super, snark for super data parallel computation super clearly. So let me see if anyone wants to ask any questions about that. If this perspective didn't make sense to you, it's not going to be a big deal. It was a way of introducing this central notion that lookup arguments are all about, kind of amortizing kind of a fixed cost that depends on the table size across many lookups. Okay, questions?
None.
Great. Okay, so here's the first baseline. So before lookup arguments were a thing, what everyone would have done, and another reason I introduced this perspective of the table containing evaluations of a function little f, is you need that perspective to even describe the following baseline. Is you just you apply, so you just apply a generic snark. Say optimize, feel free to optimize that snark for the data parallel setting. Okay, so what I mean is, in this perspective, we have the following picture. So we're evaluating f m times. The first evaluation is on A1, the second evaluation is on A2, and really, I mean the bit representation of the field element A1, the bit representation of the field element A2, and so forth. But let me just not distinguish between the two right now. And getting out these values, these evaluations. Okay, and so here, the vector of inputs is committed. The vector of claimed outputs is also committed. Right, and so now you can just apply a generic snark, GKR or something for F. Spartan, Marlin, whatever you want. Yeah. And what these will typically do is use a circuit, computing F. And basically what the prover in the snark will do is we'll wind up proving it evaluated the circuit correctly. So, really by circuit, I also mean, maybe R1CS or whatever, constraint system your snark cares about on every input A1 to AM. And the problem with this is, the prover is going to typically commit to at least, if each input to F is log m bits, F was log n bits, then the circuit needs at least linear size. So order log n field elements, per evaluation of F. Right, just because even the bit representation of each input to F is itself like in Lasso, with these caveats about they don't apply to completely arbitrary tables or something. But the same way, this circuit might not be small, log n size for completely arbitrary functions f. It's literally the same kind of caveat. So in the lookup argument, the prover, if you ignore the cost that depends on this table size, the domain of f, the prover commits to just like 3C, where think of C again as like a constant, like somewhere between 1 and 6 field elements per evaluation of f. Okay, and so that is the magic of lookup arguments. I think this is really, I really like this perspective. I hope it's coming across clearly. I didn't botch the presentation. That like before we had lookup arguments, the old way of doing this stuff was just take a circuit implementing the function that the table is storing evaluations of and apply a snark to that circuit, right? And that will always, always, always cause the prover to commit to at least, like several field elements per bit of the input to the function. Whereas with lookup arguments, the prover can commit to like a constant number of field elements, rather than a logarithmic number, per evaluation of f. Okay. Okay. So that's one naive baseline, and hopefully I've explained in what manner lookup arguments can beat this baseline. Now, they might not beat the baseline. This can actually be a pretty, especially if the snark you use is GKR based, right? GKR, if you've already committed to the inputs and the outputs, GKR will not commit to anything extra at all. It might need you to commit to the binary representation of the inputs, maybe, depending on. Anyway, I won't go into the details. So it is possible that this naive baseline is actually better than the lookup argument, especially if you're not evaluating f many, many, many times. That is, if you're not doing many lookups into your lookup table. But it's also very possible that the lookup argument beats, turning f into a circuit and applying a snark to that circuit. Okay, so that's one naive baseline. Any questions about that? And again, if that didn't make complete sense to you, it's okay. It's not central, but I think if I got the main point across, I think it's a really valuable perspective. Questions?
Yeah, there's one question, although it's not clear to me if it. So the question is simply: if the table size matches the prime field size, what consequences does that entail?
Yeah. Okay. So firstly, if the prime field size 2 to the 256, that is somewhat crazy. No one can write down a table of that size. Now,
you mean like of that scale, right? Because 2 to the 256 is not a prime, but you mean like when we're thinking in like really big number. Okay.
Yeah, exactly. Of a prime with 250, that's roughly 2 to the 256 in magnet. Yeah. So that that's way more than the number of atoms in the known universe or something. So no one can write that table down. Now that's exactly actually the kind of table that something like Lasso might look at, because often tables, you might have a massive table that is like super duper structured, and so you can describe the table without just listing all of its elements, and then Lasso is going to do a great job with that table.
So are you saying there are places where the table is that big? We just don't write it all down?
Yeah.
Okay.
It's really a matter of perspective. So in fact, when we released the Lasso paper, that we presented it in this perspective, like we can handle tables of size, 2 to the 128 or something, as long as they have some structure to them. And then if you actually kind of look at what happens in Lasso, for kind of the simplest tables, it's like it's doing very similar things to what people were already doing. And so that it's just, and there were some complaints about that. It's like, why are you presenting things in this like kind of weird way, this weird perspective, when you wind up doing something similar to what's already done today? And the answer is sort of, when you move a little bit beyond the simplest case, we're actually doing something very new. But okay, maybe there's a good, maybe it's worth having an example here. Let's say the table is the ith entry of the table is just like the field element I. Okay, where I ranges between 0 up to 2 to the 64 or something. Maybe 128, let's say that. So this table is so big, like nobody will ever be able to write down the whole table. But like it's also the world's simplest, dumbest table, right? It's just the numbers between 0 and 228 minus 1. Yeah. So in something like Lasso, it turns out like the verifier only needs to evaluate, it doesn't need to know the table except to evaluate the multilinear extension of the table, viewed as a vector, which for this table is that polynomial, let me call it T twiddle, would be, it's 128 variate polynomial, right? And it's simply sum from I equals 1 to 128 of 2 to the I minus 1 times x sub I. Okay, so the table is huge. No one can write the table down, but like the snark verifier doesn't need to write the table down. It literally just needs to, so to evaluate this thing at a random point is just like 128 field ops. Okay, and in fact, they're like really nice field ops. They're just like multiplications by powers of 2 and additions. And then, like the prover in Lasso applied to this table, basically, if you want to know what, like what the jth entry of T is, well, it's like you don't really need to like have the whole table stored. Like the prover just knows that the jth entry of this table is J, like the integer J. And in fact, what Lasso would do would be to like break the index J, which is sort of 128 bits or something, into let's say what would it be, like 8 like chunks of size 2 to the 16 each. Sort of do a lookup into of each chunk into the smaller, into the table of size only 2 to the 16, whose jth entry is also J, the field element J. And then like concatenate the results, right? Like, so big table T of J, the jth entry is J, and this J is 128 bits. And so if I break that 128 bit J up into, 8 16-bit chunks where each of these are just 16 bits each, right? Then, and I sort of, do a lookup again. It's kind of the world's dumbest lookup to figure out that the J1th entry of the small table is J1 and the J2th entry of the small table is J2. Then I can take the results of those lookups, which again is just J1 up to J8, and kind of concatenate them to get J, which is the jth entry of the big table. So, there's a perspective here which I am convinced is like really valuable, but then for the simplest tables, everything kind of simplifies and trivializes so much that you don't see the value of the perspective anymore. And so if you never look at more complicated tables than these very simple tables like this, and by the way, this is exactly the table you want for range checks. So if you're doing many range checks, I actually think Lasso, a lookup argument for range checks, and I'm obviously biased for Lasso as kind of the nicest one, but people can debate that separately. I think is absolutely the way to do range checks. Literally just do lookups into this trivial table. And so I actually think, this perspective is valuable even for these simple tables. But like, you really see where the perspective gets valuable when the tables get a little more complicated than this. So I don't know. So maybe I shouldn't have started with this perspective of, potentially giant tables, and, the lookups are equivalent to evaluating a function, at one input per lookup. It has led to sort of some confusion in public discussion and some kind of accusations that there's nothing new here. But actually, I think there is something new here. I think the perspective is highly valuable, and I hope there is value in me having presented it here today. At a minimum, I did want to. This is a valid baseline, and I don't know how I could present it. How I could have presented this baseline, that just goes through a circuit and a snark for data parallel circuit sat without using this perspective. Okay, sorry for the rambling. More questions, follow-up questions?
Yeah, there's one question that says, can lasso/ML lookups prove float 64 operations?
Yes, that is not implemented yet. I know of a project that is working through that. And short version is, I think that if you're using if your snark is using big fields, big prime order fields, I think lookups are exactly the way to implement like 64-bit floating point operations if you do want to implement them. And there's work that is going to do that in time. Sort of everything is written up, like what are the lookup tables, to implement like IEEE floating point stuff. But no one's implemented it, and that write-up has not been sort of made public yet. And that, in general, I think if snarks over fields of characteristic 2, like using the Binius commitment scheme, take off, they are actually going to make this naive baseline here much more attractive. And I actually think this baseline will actually beat the lookup arguments. Everyone's just going to do bit decompositions everywhere and like apply, circuits or constraint systems that compute, everything we care about in binary. And lookup arguments will, in a sense, go away. But as will high degree constraint systems and everything. Yeah. So that's the answer is yes, people are looking into that. No one has implemented it. And just a broader point that, if sort of Binius takes off, this naive baseline is going to become a lot more attractive and probably beat lookups. Follow-up questions, comments? Okay. I do want to say one more thing about that remark that, these binary field snarks and commitment schemes making bit decompositions much cheaper. And so just like naive approaches that we roughly knew about, 10 years ago or more, 30 years ago, but just didn't have the techniques to make them fast, suddenly become attractive. So remark, I think I meant to say this earlier. Okay, lookup arguments are equivalent, index lookups anyway. So they are like snarks for read-only memory. Okay. A modest extension of these lookup arguments actually supports read-write memory. Where just as a quick sketch, like now maybe there's you could formulate it many ways, but let's say there's 4 vectors committed. So let's say A1, V1, well, no, let's say A, V, A prime, V prime. And these are indices and values of reads into the memory, the table. And these are indices and values of writes. So the values in the table are dynamic. So it's like maybe you interpret these 4 vectors as like, the very first operation is a read, and that's given by, read of cell A1, is claimed return value V1. And then the next operation is a write. And, A prime 1 gives you the cell that's written, and V prime 1 gives you the value that's written to that cell. And then the next operation is a read, and A2, V2 gives you that read. And, the next operation is a write, and A prime 2, V prime 2 gives you that write. And so I think for so read-only memory in this like weird perspective I gave where the memory is just storing evaluations of a function. Read-only memory is sort of equivalent to like function evaluation from, this perspective. Okay. And I think snarks like Binius in the long run, once fully engineered and developed, will actually potentially just make this, circuit-based naive baseline for just implement your function with a Boolean circuit and apply a snark over binary fields to that circuit will actually beat lookups in that case. Okay, but that will not handle, like, that circuit approach will not extend to read write memory, which means ZKVMs, which really need to support, VMs, VM has a random access memory and registers, and so that's read-write memory. ZKVMs need this. Okay, which means even in a world where Binius sort of takes over, we're still going to want lookups. They're just lookup arguments. They just won't be called lookup arguments anymore. They'll actually be called like memory checking procedures, because we'll be using them for read-write memory, not for read-only memory, aka function evaluation. So no matter what, lookup arguments are sticking around. It's just they're going to be slightly generalized for read-write memory, not read-only memory. Okay, so that was one naive baseline. Just view your table as computing a function, turn that function into a circuit, apply a snark for that circuit. One invocation of the circuit per lookup. That's one naive baseline. The next naive baseline is Merkle hashing. Okay, which is say, it's a little hard to formulate when like everything is committed, but like somehow, like at all times, this is let me keep the statement vague. So at all times, like somehow we're going to maintain. Well, okay, let's say if it's read-only memory, maybe it's not hard to formulate. Read-only memory is simple. So let's say the verifier somehow obtains a Merkle hash of the table. Okay, whether an honest party computes that in pre-processing or whatever. Okay, and now, for every entry, I, the claim that T of AI, so to prove T of AI equals VI, you just provide in the proof of Merkle authentication path. For opening leaf TI. Opening leaf AI to value TI, VI. And this is fine, like it works, but it's like terrible because every lookup requires proving knowledge, proving that you evaluated a cryptographic hash, whether it's Poseidon or Blake or whatever, correctly logarithmically many times, log n times, because that's the depth of the Merkle tree. Okay, that is brutal. That's terrible. Okay, and this is called online memory checking. That refers to the fact that every single read into the memory, the read-only memory in this context, is immediately proven to be a correct read. And so conceptually, like if any read is wrong, you kind of immediately know it's wrong because the Merkle authentication path doesn't check out. And it's overkill for snarks, right? For like a ZKVM, like you don't, the prover, if the prover is honest, every single read is correct. And if it's dishonest, you as the verifier don't care which read was dishonest. You just want to reject, right? So all you care about is were all the reads correct or were one or more of them incorrect, right? So this Merkle thing will tell you like kind of conceptually like exactly which read was wrong, but you don't care in like a ZKVM or snark or whatever. You only care are they all right. And so lookup arguments are also called offline memory checking. And the point is they kind of check all of the reads for correctness all at once. And if the check fails, you have no idea which one, caused the problem or which, could be more than one, but you also don't care. So that's like kind of another word for lookup arguments. It's also used to refer to this generalization to read-write memory. Okay, so those are the two baselines. All right, so let me pause there, and then we can finally talk about lookup arguments. And let's see, we're an hour in, but that's okay. I think I can give the main idea of the lookup arguments quite quickly. Any questions?
Nope, no questions.
Okay, great. All right, so the main idea here is the following. So reduce that you want to turn, like maybe you don't like the word reduce. Let me say turn the claim that, VI equals T of AI for all I into an equivalent claim that, let's say two vectors, say, let me give them names. I don't know, E and F are permutations of each other. Okay. And so, somehow E and F are each derived from, in some way, in some relatively simple way from A, V, and T. Okay. And then, and then you just like check that claim. And we've talked about this before several times now, but now we're seeing like maybe this is kind of the big payoff for it. How do you check the claim that E and F are permutations of each other? Well, there's the typical way to do that is called Lipton's trick. That's one way people refer to it, and that is the verifier picks an R at random from the field and confirms that the product over all entries of E, let's say these vectors typically, their length might be, I don't know, maybe it's like n plus m or something. So check that EI minus R is the product, is same thing for FI minus R. And yeah, so, what this is doing is it's interpreting the entries of E and as the roots of a polynomial, and same with the entries of F. And it's evaluating that polynomial at the point R. And again, if E and F are permutations of each other, then these two polynomials are the same polynomial, and you're evaluating them both at R. And if the E and F are not permutations of each other, then these two polynomials are different polynomials, both of degree n plus m, or whatever the length E and F are. And so they're very unlikely to agree at R. And then we can just check that this equality holds with one or two grand product arguments. Okay. Right. And we've actually seen we have a bunch of choices for the grand product argument to use. We've talked about kind of two of them very recently. These would both, if you want to, if you have E1 up to En plus M, you write a circuit that's just a binary tree of multiplication gates that products everything together, in a tree structure. And you can either apply GKR or Spartan to the circuit. GKR will be the fastest. Actually, we have both implemented in Jolt repo now, and it's 10x faster than Spartan. And the GKR will have bigger proofs. Spartan will have smaller proofs but be slower. And then there's another option that uses univariate polynomials, which sort of if you kind of apply Marlin, Marlin wouldn't use a grand product circuit. Marlin winds up using what I would call like a deep circuit. The univariate techniques so you have a multiplication gate that multiplies E1 by E2, and then another multiplication gate that multiplies that by E3, and so forth. And you could apply any univariate snark, like Stark's, the polynomial IOP in Stark's, or Marlin or something to this circuit, and that will give you, depending on the polynomial commitment scheme you use, that might give you the best verifier costs, but have a even slower prover, than like Spartan. So that is the idea. Okay. So the key details to cover that we really haven't already seen is how do you turn, the original claim that every lookup into the table is correct into equivalent claim that two vectors are permutations of each other. Okay, so let me pause there and see if there are any questions about this. Okay, so so that now there are a bunch of transformations, ways of turning the original claim into an equivalent claim about two vectors being permutations. Let me. So what I want to cover, if I don't just decide I've droned on too long today, and we should actually revisit this next week, for part of the session. I want to cover aria. This is actually the first lookup argument. It introduced the notion. For some reason, a lot of people think plookup was the first. It wasn't. Plookup cites aria. So credit where it's due. I'd like to sketch plookup. Very sketchy. I'd like to sketch basic lasso. And I'd like to sketch logup. And probably that's too ambitious given the timing. But actually, these are each pretty simple if I hide enough of the detail. Like I can give the main idea for each pretty quick. Let's start with aria. Okay, so aria, the best way I know to present it is not quite to go through the permutation check exactly, but rather to go directly to Lipton's trick. So it's implicitly, there's a permutation check in there, but really it's best described by just directly going to Lipton's trick rather than an intermediate step of a permutation check that you then solve with Lipton's trick. So aria, yeah, it's almost directly Lipton's trick. So here's, let's see. Okay, so oh, by the way, basic lasso is the only one of these four that's naturally an index lookup. Like the other three are naturally unindexed lookups. So I'm going, and you can kind of transform an unindexed lookup into an index lookup without too much fuss, although it does add some overhead. So I'm actually going to present each of these in the unindexed case, but yeah, so apologies for that bait and switch. We are now going back to unindexed lookup. So for aria, the prover has committed to a bunch of values v and wants to prove that vi equals tj for some j, for I equals 1 to n. That's an unindexed lookup argument. Okay. So here's what you do. So basically, you want to. Okay, so you could sort of view it as a permutation check rather than going right to Lipton's trick. So the claim is equivalent to V is a permutation of the vector how do I want to say it? Like maybe I'll call it T star, where Ti is repeated I'll call it mi times, where mi is the multiplicity of Ti in V. Okay, so it's like yeah, so by multiplicity, what I mean is the number of times that this particular value appears in the vector V, right? So what's going on is, we have this vector V of length m, right? And, we want to show that this is the same as the vector where I kind of go through each table element. So the table has size n. I don't know, let's say n is a little bit less than m here. And so, but where I now repeat, like T1 M1 times, T2 is repeated M2 times, and so forth. Tn is repeated mn times. And each, of course, each multiplicity is at least 0. Yeah, so what's going on is, like, if there's any entry in V that is not in T, there's no way to make this vector that I described here a permutation of V, just because this vector, by definition, the way I define this vector, all entries of this vector are in T, are in the table. Yeah. So the worry is, if the prover's lying, in its initial claim, the lie would be there's some entry V that's not in T. Then there's no way that V can be a permutation of this vector, because by design, each entry of this vector is in T. Okay. So that's aria. Okay. In a sentence, but I hid something here. So let me call this vector. I call it T star, right? So if you apply Lipton's trick to check that V and T star are permutations, you run into a bit of a problem. Permutations. Okay, because it's easy to, Lipton's trick says, hey, pick a random R, have the verifier pick an R from the field, and confirm that the product of Vi minus R, as you iterate over all entries of V, is the same over product over all entries of T star minus R. Okay, so here's the problem is, at the end of the grand product, so you can apply a grand product argument to compute this. At the end of the grand product argument, let's say it's GK or Spartan, the verifier has to evaluate at the end of the grand product argument V twiddle at a random point, and that's fine, because V would have been committed with a multilinear polynomial commitment scheme, and we're good. Get it from the commitment to V. Okay, the problem is T star is, like, not committed. Like, at the end of the grand product argument, the verifier needs, the multilinear extension of T star at a random point. And, like, how? How's it going to get that? That's a big problem. And the way aria does this is the following. It actually has the prover. So yeah, this is a big problem. Like, basically the verifier just has no access to the multilinear extension T star because of this weird way it was defined, where each entry of T was repeated some multiplicity number of times, but the verifier doesn't know the multiplicities. Okay, so what aria does is P commits to the binary representation of each multiplicity. Okay, so that's, the multiplicities are numbers between, like, 0 and number of lookups, which is little m. So that's, that would be log little m bit, committed, for each lookup, for each table entry. Okay, and this product here is the same as, the product over all table entries, I equals 1 to capital N, of the ith table entry minus R to the multiplicity, the ith multiplicity, right? Basically, this product with T star, by definition, T star has the ith table entry repeated mi times. And so you get the ith table entry minus R mi times in this product. And so I just wrote the product a different way here. A product over all table entries of Ti minus R, multiplicity many times. And so the reason in aria the prover has to commit to the binary representation of these multiplicities is because of this power here. if it committed to these multiplicities as like field elements, the field element, 3 representing multiplicity 3, the field element, 5 representing the number 5, there's no like circuit of multiplication gate, like, ti minus r to some field elements is not a low degree function, right? This is not something you can like easily prove in a snark. So basically what ARIA does is it writes a circuit that takes as input these so here we have like the binary representation of M1 up to the binary representation of the nth multiplicity, and the circuit will just compute for each of these, so this will be T1 minus R to the M1, and the circuit computes, Tn minus R to the Mn, and then just multiplies all of these together with your grand product argument. And maybe I'll just put a big box there that says, now you're good to apply the grand product argument here. Grand product. So that's the headache and the overheads in ARIA. This is why people do not use ARIA today. It's a brilliant contribution, but this vector T star is defined in a sufficiently like snark unfriendly way that it forces the prover to commit to a log m bits for each lookup to specify a multiplicity, and thereby give the verifier appropriate access to this vector T star to ultimately apply the grand product argument. So you would like, ultimately what ARIA would do is like apply something like GKR based snark or Spartan or something to the circuit where you have your grand product here, but there's like an expensive pre-processing step to compute each term, each entry of T star that's getting multiplied together or whatever. And at the end of GKR or Spartan or whatever, the verifier needs to evaluate the multilinear extension of this thing. And that, again, that's fine. You can get that from the commitment scheme. So the verifier can, at the end of this, invocation of GKR or whatever, can get, the MLE of this vector evaluated at the necessary random point directly from the commitment to this vector. Okay. So to summarize, because I didn't present it that clearly, what ARIA does is it says, hey, the prover's original claim that every entry V is in the table is equivalent to V being a permutation of this vector derived from the table that repeats each table entry some, non-negative number of times. Okay, and so then you can just do a permutation check on those two vectors, but you run into this super nasty issue that, this vector that repeats every table element some non-negative number of times is like a grossly defined vector, and it adds a lot of overhead to get the verifier like kind of an appropriate description of that vector. Okay, that's ARIA. Apologies that my presentation was a little, stunted there. Does anyone want to ask a question about that?
There's a few questions, so I'm going to go through them. I think they all apply. The first is, so T star is n plus m.
Oh, the length of T star, it's a little. The length of T star is just exactly m, the number of lookups. So T star is just like the looked up values, but sort of reordered to be grouped by table element. And so if there's a table element that is never looked up, it does not appear at all in T star. So as an example, a quick example, which I guess I should have done earlier, just really small example. Let's say the table is, 7, 3, 1, and the values are, let's say there's 4 values looked up. And let's say it's 3, 3, 3, 7. Then T star would be, well, okay, let me reorder this stuff. That made T star and V the same, which I think is not very instructive. Let's say it's, let's say it's 3, 1, 3, 1. Let's do it that way. Then T star would be, yeah, all right. So it would just be 3, 3, 1, 1 or something like that, right? Because 7 appears 0. You go through the table one entry at a time, and 7 appears 0 times, so it doesn't appear at all in T star. 3 appears twice, so it appears twice in V, so it appears twice in T star, and 1 appears twice in V, so it appears twice in T star. So this is like it's like T star just is V in sorted order. So, but sorted by like the table itself, specifying the that 7 comes before 3 comes before 1 or something like that. Was that helpful? Did that clear things up?
I don't see a reply in chat, so I'm not sure. Yeah, so yes, it did. And is T star essentially okay? T star is essentially a sorted B, and then the last question was: should the MI greater than or equal to 0 be an MI greater than 0? This is
Good.
yeah.
So the issue is, the reason I said greater than or equal to 0 is this example, 7 is in the table but never appears in V at all, so its multiplicity is 0. Right. And so I went through the way I defined T in words here was I went through each and every table element, including the ones that don't appear in V at all, and said that table element appears MI times. And so some of the MIs will be 0, according to that definition. Some table elements might not appear at all in V, then their multiplicity is 0. Does that?
Yeah. Great. Thanks. I feel like he just dropped off, and I don't know why. I don't think I did it, but let's see.
Hello? Can you hear me?
Awesome. Yeah. Welcome back.
Thanks, Avi, for messaging me. That was bizarre, and I did not know it happened. So was did I drop after I finished answering that question or no?
You were mostly done, I believe.
Okay.
You had explained that you were basically including the ones that that had no multiplicity, but we wanted to include them so that you had to greater than equal to 0.
Yeah, and what's going on is like you need this circuit here to the verifier needs to know what the circuit is, and the verifier does not know which which table elements appear in V 0 times, meaning not at all, or more than 0 times. And so you really need a multiplicity provided for each and every table element. You can't have the length of this vector and how to interpret it depend on V. So in order for the circuit here to be independent of V, you need one multiplicity to be provided for each and every table element, whether or not they appear in V at all. And so the ones that don't appear in V, the multiplicity of 0 has to be provided, and in binary, which means just log m 0, 0, 0, 0, 0, whatever log m zeros.
Another question: how does the verifier calculate the V product part?
Yeah. So you use a grand product argument for that. So that's what I was saying up here, where I said you have we've seen several options for grand product arguments. One is, or two, you basically take a circuit computing the big product and apply a snark to that circuit, but you're free to optimize the snark heavily given how nice structured the circuit is. So what's going on is the inputs to the circuit for V, like, the inputs to the circuit are, like V0 minus R is the first input, V1 minus R is the second input, up to Vm minus R. And so, you, at the end of, like, let's say you apply GKR, to this circuit that just does a binary tree multiplication gates to multiply all this stuff together. At the end of GKR, the only information the verifier needs about the input to the circuit is a random evaluation of the multilinear extension of this vector here. And this evaluation, is easily, that evaluation is easily derivable. So, okay, so let's call this vector, I don't know, V prime. Okay, so the multilinear extension of V prime evaluated at a random point R prime is just the multilinear extension of V, which has already been committed at R prime, minus R, right? Because V prime is literally like viewing V prime as a vector. That vector is literally just the vector V, entry-wise minus R. And so the multilinear extension of, it's like the multilinear extension of V minus, R times the constant one function, anyway. So this is it. So you just apply a grand product argument to product all these things together, and the information the verifier needs about the input to this grand product is easily derivable from the commitment to V twiddle. Did that answer the question?
Yep. All right.
Is that all the questions?
I had a quick question, Professor. So, is this because you keep saying that this pre-processing is very expensive? I'm just curious to know: is this reusable across multiple rounds?
Which pre-processing?
Pre-processing of committing to log m number of bits.
Okay. So that's not pre-processing in the sense that these multiplicities. That's not pre-processing. That is done. These multiplicities depend on V. And so the table is sort of, we think of as basically fixed in advance typically. But V is not, and like in applications, V will, like in a ZKVM, V will wind up depending on, like the particular run of the computer program that the prover is proving it ran correctly. So it's not pre-processing. It is just an expensive step in the snark. And yeah, I mean, the way to think of it is, exactly how expensive it is to commit to these multiplicity, the binary representation of these multiplicities obviously depends on which polynomial commitment scheme you use to commit to them. Okay, but if you use like a group-based polynomial commitment scheme like KZG or bulletproofs or something, it's roughly going to be one group addition per one in the multiplicities, which like in the worst case is, what would that be? Like m times log m group ops, which is not good. Like we really want to, like the goal should be to avoid this log m factor. And if you use like a hashing based commitment scheme like Fry or something, you're still, committing to one field element per, each of these m log m bits or whatever it is, and actually in that case, it's really, you pay for the zeros as well. So that would be n log m bits, or sort of maybe the max of m and n, I don't know. And yeah, so maybe, I don't know. Maybe this is like the min of m and capital N. I don't know. And that's all. So that's going to require an FFT over a vector of length n log m, and hashing everything that comes out. And again, it's just this log m factor is just not nice, really. we'd much rather sort of commit to only, like a constant number independent of m many values per lookup. But yeah, like, even naive baselines can be surprisingly hard to beat. So people don't use ARIA today, but maybe there are situations where it wouldn't be a terrible idea. Yeah, did that make sense?
I'm trying to understand. I understand what you're saying. So, are you saying that across distinct V, this particular commitment of m log m bits is not going to be reusable? But is that
Oh, I'm
this?
sorry. Yeah, this is exactly. This is every time V changes, you're going to have a brand new commitment here, right? This commitment, like the vector here, depends on V, right? Like the ith entry of this vector is the number of times that the ith entry of the table appears in V. So you change V, or at least you change, you do more than reorder V, you change the multiplicities, you're going to have to have a new commitment, Yeah.
So, within the same V, it is indeed reusable.
You're saying if you change the table, but not. So it depends on
Not the
V
V.
and T. Yeah. So it's the number of. It's the multiplicity is the number of time each table entry appears in V. So if you change V or the table, this multiplicity vector changes, and you're going to have to, have a fresh commitment to the multiplicities.
I see. Okay. Thank you.
Yeah. Great. I mean, let me also say, like, but while we're talking about how, how bad is this, committing to log n bits per table element or per lookup or something, there are some like bit decomposition, just having the, going back to the naive baseline of, of evaluating this function f over and over again. If you view the table as storing evaluations of f, that would require committing to the binary representation of each index that's getting looked up, that is each input to f. And generally people think, like we've been doing we've considered committing to bit decompositions as like a naive baseline, like that's the dumb way of doing things. We've been thinking that since people started implementing these snarks, 15 years ago or however long it's been now. And it can be surprisingly hard to beat. And I think some lookup arguments that got a lot of attention actually typically don't beat that. And I think as Binius gets, more developed, I think, bit decompositions are actually going to be optimal for read-only memories or function evaluations. They won't be optimal, again, for read-only memories, and you're still going to basically want the lookup arguments. So committing to what ARIA does of committing to the binary representations of these multiplicities might not be that bad. Okay, in the end, it is log m bits getting committed per table element. But something like Binius commits to bits really, really fast. It'll pack those, each of those log m bits into a single field element, and then sort of, turn all of those log m bits into the you commit to them with the cost of committing to one field element instead of log m field elements or whatever. So anyway, so ARIA maybe deserves more love than it's getting these days. Okay. More questions? All right. So I know I'm, way over time. Let me just say, lookup and logup can both be viewed as optimized variations of ARIA. Now, I don't think people do view them that way, but I think they should be. Okay. So let me just say, lookup, the prover actually commits not quite to T star, so to a vector very similar to T star. Okay, remember T star had length m, right? T star was just like, it was V, the value vector, but like, resorted, kind of grouped by table element. Okay, and Lookup says, hey, Aria ran into these problems. This problem that it had to commit to the binary representations of the multiplicities because T star was gross. It was defined in this weird way from T and V, and in order to give the verifier like access to the right low degree extension, evaluations, we kind of have to have the prover specify T star by like giving the binary representations of these multiplicities. We don't like that. So in Lookup, what the prover commits to is the vector of length m plus n, which is the table itself. Okay, let me put it this way. It's just it's T star, but with multiplicity, I replaced by mi plus 1, right? So it's like we're going to make sure every table element appears at least once in so let me call this, I don't know, T star star, just to emphasize that it's very related to T star. Make sure each table element appears at least once. So it's like these zeros that were asked about before. Do you even need to commit to the zero multiplicities? They kind of intuitively, if you, from the Lookup perspective, are the whole problem with ARIA. That's why we needed, binary representations of the MI somehow. So if we make sure every table element appears at least once in T star star, then somehow life gets a little easier. Basically because you kind of, I don't know, conceptually, if you want a little intuition, I guess it's because you don't have to like take some table entries and just get rid of them completely. It's like everything appears at least once. So basically, so the check in Lookup is to check that the looked up values followed by T is a permutation of T star star. Okay. And again, so now this T star star is sort of grouping, not V itself by table element, but VT by table element. Okay. And then Lookup just has a clever way of dealing with things, right? So like T star. So now I'm going to hide the details, which actually I'm not sure I could have even given unlimited time. I'm not sure I could present them in a super intuitive way. But basically, you roughly apply like Lipton's trick to this permutation check, but in a apply Lipton's trick to do the permutation check in a clever way. So it's a variation really. So it's a clever variation, so that V does get like the prover's commitment to T star star is enough information for V, so that it all works out. That's a very hand wavy thing to say, but yeah. So so let me just try to summarize that. Yeah, so sort of what actually gets grand producted in Lookup, rather than the entries of T star star itself, you sort of look at so in Lookup internally, maybe this just won't make sense and I shouldn't even say it, but you sort of replace T star star of I. So you don't apply Lipton's trick like directly. You sort of do it in a slightly indirect way. So you replace the ith entry T star of I with sort of the difference between the next entry of T star star and the ith entry. Okay, and that means that if well, okay, it's not going to be helpful. I'll just stop there. So yeah, so all I want to say about Lookup is it's somehow able to get rid of the binary representations of multiplicities by replacing T star star with a longer vector. But it's otherwise the longer vector is very similar to T star star. It's like rather than apply Lipton's trick to V itself and T star, you sort of append the table to V and then group that larger vector by table element. Okay, so that's lookup. Sorry, it's so hand wavy. Should have taken more time to think through how to present it. And then logup uses the following identity. So I'm just going to state it. It is that the sum from J equals, so the sum over table elements of the multiplicity of the jth table element over the jth table element itself plus x, this is like a variable, equals the sum over entries of V, so there are m of those, of 1 over that entry of V plus x. If and only if the original claim is true. So, the entries of V are all contained in the table. So this comes from something called logarithmic derivatives. I view it as like a clever way of modifying aria because you still got these multiplicities here. And what the prover does in logup is the prover commits to the multiplicities, but now not their binary representations as field elements. Not the binary representations, right? So if the multiplicity of something is 3, you literally just commit to the field element 3. Okay. And the verifier picks R at random from the field and confirms that, just checks this equality holds at R. So sum over table elements of MJ over TJ plus R equals sum over entries of V of 1 over VJ plus R. And, so you apply your favorite snark basically to compute, this sum and this sum. And, we, in general, we don't like division in snark. So, you'd actually clear denominators. So you what you'd really do is you'd confirm, you kind of multiply both sides by the product of these TJ plus R's, and you multiply both sides by the product of these VJ plus R's to clear the denominators. And now that starts looking a lot like a grand product. And so, you kind of do the same, pick your favorite grand product argument from the grand product argument choices we saw before. And, at the end of the day, you wind up just having to evaluate, like some low degree extension of M at a random point, some low degree extension of the table at a random point, and some low degree extension of V at a random point. Okay, that's logup. So it kind of takes aria to it's a really nice, in my view, like perfection of aria. In that, like, the problem with aria, the reason people don't use it today, the reason people didn't just stop designing lookup arguments with aria is that you have to commit to the binary representations of these multiplicities. And logup just directly gets rid of that. You commit to the multiplicities as field elements, and that's it. It does have extra expense in that you have to compute, these sums of ratios. And so I will come back to that extra expense in a moment. But when I saw logup, I was like, this is like a really cool, whenever anyone who read aria and understood what was happening there, like, this is exactly what they wanted to achieve. If you just look at the commitments, that we didn't want the binary representations of the multiplicities to be committed. We wanted the multiplicities to be committed as field elements. Perfect. Okay. But, in the end, I think actually, logup has downsides because like the snark you have to apply to check this equality after the multiplicities are committed winds up being fairly expensive. Also, it's sort of an unindexed lookup argument, and you can turn it into an index one, but it adds some overheads and stuff like that. Okay. Does anyone ask any questions about that?
Nope, don't see any.
Great. Okay. So I am going to sketch lasso, and very sketchy, and then we'll be done. So lasso is naturally an index lookup argument. Unlike everything else we discussed today, again, most lookup arguments in the literature are naturally unindexed. I think the main example other than lasso might be Baloo. Anyway, so lasso is naturally an index lookup argument, and it tries to say the following. So it kind of says, look, I have the table T on one side of the world, and I have. Oh, sorry. Let me. Yeah. I need the indices. So I have like tuples, like 1 comma T1, 2 comma T2, kind of like a specification or initialization of the table, n comma Tn on one side of the world. And on the other side of the world, I have the lookups into the table, so I have like A1 comma V1 up to AM comma VM. Okay. And so I want to make sure that, T of AI equals VI for all I equals 1 to M. Okay. And I want to turn this into a claim that is equivalent to I want to identify two vectors that are permutations of each other if and only if indeed, T of AI equals VI for all I. So what am I going to do? I'm going to start adding elements to both the left side of the world and the right hand side of the world in an effort to develop two vectors that are permutations of each other if and only if the lookups are all valid. Okay, so in a perfect world, what I would do is I would just I would add. Yeah, let me draw some boxes around these. So this vector of tuples, I put an orange box around. Sorry, that wasn't a great choice. But let me stick with orange there. And let's see, this side of the world, I'll do purple. Okay. So what I'd like to do is just sort of add the purple vector, append the purple vector here and append the orange vector here. Okay. And then I'd be done, right? Like if I could somehow do that. Like, so if the verifier could have, am I saying this right? Maybe I'm not quite saying this right. No, I didn't quite say it right. Okay. Yeah, that would trivially make them permutations. That would be too sorry. Those would trivially always be permutations of each other, of course. So, all right. I thought I had a plan to describe what's going on intuitively, and maybe I botched it. Okay,
I think it would be reasonable. It might be reasonable to stop here, right?
Stop here.
We're at about
Okay.
2 hours, and then we can, you and I can chat and make a better presentation of the thing instead of trying to figure it out.
That's okay. What I'm going to do is I'm going to limit myself to 90 seconds, and then we can chat. And if desired, I can revisit. So 90 seconds. Here we go. So we think of this as initializing memory. We think of these as reads into the memory. Okay. What we're going to do is sort of artificially add writes to the memory in addition to the reads to the memory. Okay. So that every read to memory is followed immediately by a write to the memory. Where the write, so if a read, to cell AI, A1 returns value V1, the write is sort of forced to be the same. So you write back the same value. But yeah, that's it. And so yeah, that does lead to the sort of trivial permutations. It's why it doesn't quite work out as stated. So what we wind up doing is every read operation, we sort of add to it an extra piece of data. to make this attempt at, identifying, these two vectors that are permutations of each other, if and only if the reads are correct, we add an extra piece of data to each read called an access count. Okay, so the prover commits to these access counts, one per read. And now every write, every time you do a read that returns a value v1, say, and a count c1, it's immediately followed by a write to the same address. You write the value returned from the read to that address. So if the prover's honest, it doesn't change anything because that value was already there, but you increment the count by 1. Okay. And then, so that the idea is we sort of try to get an entry over here on the left side of the world that sort of matches an entry on the right side of the world. Except the count is incremented by 1. And then now we want to do the same to get, an analog of the initialization of memory over into the right side of the world. And so we have the algorithm, the entity doing the reads into memory, sort of do one final pass over memory that's meant to sort of offset, sort of match the initialization of memory. So, by the way, the memory gets initialized to all have count 0. And so, and then we do one final pass over memory, where we read each memory cell. Memory cell 1 with some value, that the prover claims is in that cell, and a final count. So C1 final and C1 final, up to memory cell n, value n final, count n final. Okay, and this actually works out, even though I know you didn't follow it and I need to stop speaking. It turns out that all of the reads are correct, okay, if and only if there are tuples you can put here for the writes and tuples you can put here for the final pass over memory, so that the left-hand side and right-hand side are permutations of each other. Okay, so in Lasso, the prover winds up committing to these counts, these extra counts. These extra writes and these final pass over memory things, and then you just do a permutation check and that's it. Okay, so let me stop there. It's sort of just is more of a departure from ARIA than Lookup and Logup. So harder to explain. And I will ponder a better way to explain it next time and either just skip it or try again. So thanks for bearing with me today. And I will stick around for final questions if there are any.
Awesome, thanks. One question at least. Hey, Cosmo, you want to speak? You are on stage.
All right. Well, we can take it async if there's technical issues, or if I just went so long the question went away.
Yeah, I think technical issues. Yeah, go ahead and stop here.
Okay. Well, let me just say one more sentence because it's not super technical, and then maybe if anyone thinks of a question, they can ask it. So, quick comparison just between the cost of Logup versus Lasso. So Logup seems to be really popular now. People seem to think it's a incredible lookup argument. And like I said, it sort of on its surface seems perfect, because it's exact. If you just look at the commitment cost, it's exactly like a perfection of ARIA. ARIA was committing to the binary representation of these multiplicities. Logup sort of, it just commits to each multiplicity as a single field element, and that's great. So there are two counterpoints. So one is if you're naive about Logup, you actually also how you prove this equality here. You actually do have to have the prover commit to these inverses, these ratios, and also these are random field elements because they have this plus R in there, and committing the random field elements is really slow. And whereas Lasso, the prover never commits to random field elements, it just commits to these counts. Like the indices and values are already committed, and then the only extra stuff getting committed in Lasso is these counts, and these counts are always small. So now there is a variation of Lookup that uses GKR to check this equality holds, and that gets rid of the need to commit to these random field elements. Okay, but that comes with its own downside, whereby the number of multiplication gates in the circuit that GKR gets applied to is at least 3 times the number of multiplication gates in the grand product circuit that arises in Lasso. Okay, and so my view is the following. The Lookup actually has better commitment cost, like Lookup with GKR actually has strictly better commitment costs than Lasso. Okay, but it's sort of a marginal improvement, whereas for each multiplicity, Lasso would commit to the numbers like 1, 2, 3 up to that multiplicity. Lookup just commits to that multiplicity. And there's a lot of other stuff getting committed in any snark that's using these lookup arguments anyway, and like this committing the 1, 2, 3 up to mi is just not a bottleneck compared to committing to it's just not a big deal. Whereas the extra field work in the GKR protocol applied to compute these weird, sums of inverses is significantly more than the field work in GKR applied within Lasso. And so in Jolt with our lookup arguments, in Jolt, the commitment costs don't really for these multiplicities are not a major cost, but the field work in GKR actually is. So it'd be worse to 3x or 4x that field work to save some commitment costs that don't really matter. So that is sort of I think the community is sort of missing that. You're sort of one cost gets better, but another cost gets worse, and it's actually the cost that's getting worse that matters. So maybe people will come around to that at some point. Okay. So last chance for questions, and otherwise we'll wrap up.
There's several questions now.
Oh, now there's several. Okay, sounds good.
The first is the one that Kuzmo had come on stage to try to ask. So, is it possible to check the permutation of 2 vectors using matrix permutations? Are there any existing uses of matrix permutations for comparing 2 vectors? And is there a advantage between the 2 methods?
So I don't actually know what a matrix permutation is.
I also wasn't sure what that meant.
Yeah. So maybe.
Maybe permutation matrices. I don't know.
Interesting. I haven't seen anything like that. I don't know. So the short version is, I can't really answer, without knowing for sure what's being referred to, but whatever it is, no one has used it. So if there is a use for it, it would be new and interesting. That's the best I can say.
Next question is, what about quarks for proving the grand product? What does it do differently than the GKR approach?
Oh, great. Wonderful question. So, so in both cases, you just have this binary tree of multiplication gates. So let's say you want a product, I don't know, just B1 up to BL. So you just have this circuit that does it via a binary tree. And what GKR will do is, let's imagine that B1 to BL are already committed, because that's always the case in these lookup arguments. And GKR will not have any more commitments. It will just apply GKR to this circuit, and that's it. What Spartan or what Quarks will do is commit to the value of all these multiplication gates, which you should think of as partial products, and that is really expensive. It's 10 times more expensive for the prover than just running GKR in our implementation within Jolt today of both lookup arguments. Because what's going on is in these grand products, really, each entry of BI is some already committed thing that was small, but minus a random R, right? So these partial products are random field elements, and so if you commit to them, it's really expensive. Whereas without committing to that, that's the only point in the entire Jolt ZKVM where random field elements would get committed, really. So but the benefit of Quarks is the proof size is only logarithmic. You apply one sum check for the whole grand product circuit rather than one sum check per layer of this binary tree. And so it's a significant reduction in proof size. Now, Quarks, I'm not even sure that the Quarks authors, even though one of them is the Spartan author, Srinath, are aware of this. But Quarks really is just, the Quarks is Spartan applied to the circuit, to like the natural R1CS implementing the circuit, and then like optimizing the protocol given how incredibly structured and simple this circuit is. And so you actually see this. I really was not aware of this until somewhat recently. When you apply Spartan to highly uniform constraint systems, like Spartan in general for unstructured constraint systems, it needs 2 sum checks. Okay, but when the constraint system is highly uniform, you actually get rid of the second sum check completely. And so Quarks, it kind of, they didn't realize they were doing this, I think, but they sort of, it's the same protocol you get when you say, well, let's apply Spartan to this circuit, this great, binary tree of multiplication gates. And then let's look at the fact that, the constraints here, this circuit is so structured that you can actually just get rid of the second sum check. And if you go through that exercise, what will come out is the grand product in section 5 of Quarks. And then section 6 of Quarks is sort of a hybrid between GKR and section 5 of Quarks, where you sort of Spartan the many small layers of the circuit near the output, so you're not applying sum check so many times. But then GKR a handful of big layers near the inputs. And the idea is that way you only apply GKR like 3 or 4 or 5 times rather than 20 times or 25 times. But you nonetheless avoid, so you get the verifier benefits of not applying sum check so many times. But most of these product gates are in the handful of layers near the inputs, right? Just because binary trees have almost all their leaves, near the all their nodes. There's like twice as many leaves as there are, parents of those leaves, and then twice as many of those nodes as their parents, and so forth. So hopefully that explains the difference between GKR and Spartan. It's a prover time versus proof size tension, different points in the trade-offs.
Next question. The asker was quite happy with that answer. Next question. Where, if anywhere, would Coq fit into this taxonomy of lookup arguments?
Great. So I would say so Coq sort of set off a line of work that I think you can view CQ as like the ultimate culmination of that line of work. So let me tell you what CQ does. Okay, so it moves all table size dependent costs to a pre-processing phase that depends only on the table. Okay. Now this pre-processing is like really expensive. But you only have to do it once for any table. It's like generating a power to tau SRS. Kind of any snark with KZG commitments can use that. Forever and ever and ever. And similarly, this pre-processing, any snark that wants to use CQ for a given table can use pre-processing forever and ever and ever. And so it's like n log n, group exponentiations, also known as scalar multiplications, in this pre-processing. And the prover stores the data structure of size n. So like if your table is really big, that's also maybe problematic. Okay, and then after that pre-processing, the cost per lookup for the prover is only committing to about 7 random field elements per lookup. Okay. So it whereas Lasso's cost to, is like some table size thing. Maybe, if it's a somewhat structured table, you can get a 1 to the C here, plus, C times 3 times M or something. So in something like Lasso, there is a cost that depends on the table size, albeit potentially, sublinear in the table size. And whereas here there, and then there's a per lookup cost, which is like 3C committed field elements per lookup. In CQ, the cost is complete after the pre-processing is done, is completely independent of the table size. Okay. And at a high level, I think what CQ is doing is it's looking at lookup, and it's saying, is it log? Yeah, I think it's inspired by lookup, I think. And it's sort of saying, hey, look, there's a bunch of like ratios in here. And I'm waving my hands like crazy, and I haven't looked at CQ in a while, but it's sort of saying you can kind of pre-compute one ratio or something per table entry, so that you wind up like this sum gets handled, like with there are capital N terms in the sum, like one per table entry, but like any table entry where nj is 0, like you can just ignore, because the 0 over anything is 0, and so it doesn't contribute anything to the sum, and so that's why it's able to get online costs that only depend on m and not n at all, something like that. Waving my hands like crazy, and apologies for probably saying something a little bit inaccurate. So you could say CQ, Calc led to CQ. CQ is some variation of the ideas in lookup to get all table size related costs to pre-processing. Now, I just want to say one thing here. 7 random field elements is sort of equivalent in cost to committing to like 7D or so small field elements. Okay. And I actually think that in a lot of applications, if you just do things via bit decompositions instead of lookups, like this naive baseline I described before, where if your lookup table is storing, I don't know, numbers between 0 and 2 to the 16 minus 1, and you can kind of replace lookups into that table by just committing to like 16 bits per per element you're range checking, then actually the bit decomposition involves committing to only small field elements because they're all zeros and ones, and much less than 70 of them. So CQ has this like sort of amazing online cost in that it's completely independent of the table size. But then I think like concretely, when you get down to it, because random field elements are so expensive to commit to, it doesn't really, in a lot of settings, beat kind of more naive bit decompositions, and I suspect that's why it hasn't really, been deployed widely. So hopefully that overview of CQ is helpful. Yeah.
Cool. Coming back to the question about the matrix permutations, I think the question is essentially, instead of P proving that they know a polynomial that vanishes at the elements of U, instead he proves that he knows a matrix A such that AU equals B.
Oh, okay. Yeah, so that's actually how like Baloo and Lasso work. So I'd say that has proven useful, but then ultimately at some point within Lasso, you wind up with the standard permutation check anyway. So how do I want to say this? Okay, so the way Lasso gets costs that are like n to the 1 over C plus 3 times C times M, many like committed field elements or whatever, you can kind of view it as a 2-step procedure where first we kind of reduce a lookup into a table of size n into C lookups into tables of size n to the 1 over C. Okay, and actually if you, there's something in Lasso called generalized Lasso where that reduction is like very, it sort of applies to like any lookup table with any kind of reasonable structure you could possibly imagine, because it uses the most powerful technique that I in my entire arsenal, which is of course the sum check protocol, to do the reduction. But then like in JOLTS, it turns out the lookup tables we need to deal with are so structured, you don't even need the sum check protocol. And it's sort of, there's a much more straightforward way to turn one lookup into the big table and to C lookups into tables of much smaller size. Okay, but anyway, in general, like kind of the way, at least in generalized lasso, the way this reduction works does exactly what you just said. You know, there's like a permutation matrix situation going on. Okay, but then the way we handle the lookups into the small tables, to those we apply what I call basic lasso today, and which I sketched, you know, horribly. And that has costs like table size, you know, plus, I don't know, three field elements committed per lookup. And there, this is just like a permutation check. You know, basically just like a grand product. That's it. So I think the answer to your question is the permutation matrix thing has been exploited, but at least I don't have Baloo cached in my head. So that, at least in Lasso, the way I think we exploit that, if I remember right, is in turning like lookups into a big table into several lookups into smaller tables. But then when we actually go to, you know, handle the lookups into the small tables, now we're just doing a permutation check. So maybe have a look at the intro of the Lasso paper, and you will see this permutation matrix coming up. You could also look at Baloo if you find that easier to read.
Cool. Happy with that answer, and that is the last question.
Wonderful. All right. So thanks as always, and I will see you next week, and we will turn to ZK. So kind of exciting to finally get that topic. See you soon.
Thanks.